Alright, this is the second day of day 6 in our notes, and we're going to be looking at how to graph and analyze absolute value functions. So again, just to refresh your memory of how to graph a piecewise function, we're going to start by making a table. So for 2x plus 1, we'll have a table. And for negative 2x plus 3, we'll have a separate table. So 1 is our dividing number. It's going to be defined in the second one. It's not going to be included in the first. So we'll pick numbers to the left of that. Pick numbers to the right of this one. Alright, so 2 times negative 1 is negative 2. Negative 2 plus 1 is negative 1. 2 times 0 is 0. 0 plus 1 is 1. 2 times 1 is 2. 2 plus 1 is 3. And then run 1 through the second function. Negative 2 times 1 is negative 2, and negative 2 plus 3 is 1. Negative 2 times 2 is negative 4. Negative 4 plus 3 is negative 1. And negative 2 times 3 is negative 6. Negative 6 plus 3 is negative 3. So now I have 6 points to plot. Negative 1, negative 1, 0, 1, and 1, 3. That one will be an open circle. The rest of these will be on the line. Look like that. And then I have a point at 1, 1, and it is defined. And 2, negative 1, and 3, negative 3. And that one will be going down towards negative infinity as I continue on towards positive infinity. Alright, so today we're going to turn our attention to absolute value functions. Absolute value functions is a function that contains an algebraic expression within absolute value symbols and can be defined and graphed as a piecewise function. And the parent function of an absolute value function is f of x is equal to the absolute value of x. So we're going to graph the absolute or the parent function of absolute value, and we're going to do that by making a table. So we'll just run each number through our function. The absolute value of x is what f of x is equal to, or y is equal to. So the absolute value of negative 2 is 2. The absolute value of negative 1 is 1. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. So now we're going to plot those points. Negative 2, 2. Negative 1, 1. 0, 0. 1, 1. 2, 2. And you'll see this is going to continue on forever in that direction, and also continue on forever in that direction. And that's what the parent function of f of x looks like. Or f of x equals the absolute value of x looks like. Now, we can make transformations to this as well. We can alter the way this looks. Alright, so the way we can alter this is in 4 different ways. Alright, the first is we can have a horizontal translation. We can move this, obviously, we can move this to the left or right. And we do that by doing a horizontal translation. So x minus h means we're going to shift right. And x plus h means we would shift left. Whatever h is, we shift that many spaces. So if it was absolute value of x minus 3, we would shift 3 units to the right. If it was x plus 3, we would shift 3 units to the left. Then the plus k goes at the very end, it's the tail, and that's how we move the vertex or that turnaround point either up or down. Right? So if it is plus k, we're going to shift up. And if it's minus k, we're going to shift down. And we'll spend some more time going over this later. But just wanted to start to show that to you today. So, graph the following: the absolute value of 3/4 x plus 3. Alright, so we are going to make a table of x's and y's. And again, I'm going to pick numbers that are divisible by 4 just so that it's easier to graph. So I'm going to pick -8, -4, 0, 4, and 8. And then I'm going to run those numbers through the function. So 3/4 times -8 is going to be -6. And the absolute value of -6 is 6, and 6 plus 3 is 9. When I run -4 through the function, 3/4 of -4 is -3. The absolute value of -3 is 3, and 3 plus 3 is 6. 3/4 of 0 is 0. 0 plus 3 is 3. 3/4 of 4 is 3, and 3 plus 3 is 6. And 3/4 of 8 is 6, and 6 plus 3 is 9. So now I have 5 points I can plot. So -8, 9, that's going to be just a little above our graph. -4, 6, so still pretty high up there. 0, 3, then I have one at 3, 6, or sorry, 4, 6. And then 8, 9. Alright, so our graph looks like that. And it would continue on forever to left and right. So that means our domain is -infinity and +infinity. Our range, it doesn't go any lower than 3, but it does go up to +infinity. So from 3 to +infinity, the vertex, that turnaround point, you see it's at 0, 3, which, if you'll notice, might have something to do with that 3 there. The slope to the right of the vertex is +3/4. Slope to the left of the vertex is -3/4. So, to write f of x as a piecewise function, we would say that f of x is equal to, we need our little set sign, -3/4 x plus 3 for x is less than or equal to 0. And we would say +3/4 x plus 3 for x's greater than or equal to 0. So that is how we're going to define that as a piecewise function. If you'll notice, it has a -3/4 slope on the left side until you get to 0. It has a +3/4 slope on the right side after 0. And then the lowest those get is at that 3, 0 point, or 0, 3 point, excuse me. So that's how that works. All right, the next one, graph the following: f of x equals the absolute value of x minus 1 plus 3. So again, we're going to make a xy chart and pick some x's. This time I'm just going to pick numbers in the middle. And then run each of those through the function. Negative 2 minus 1 is negative 3. The absolute value of negative 3 is 3, and 3 plus 3 is 6. Negative 1 minus 1 is negative 2, and negative 2, the absolute value of negative 2 is 2, and 2 plus 3 is 5. 0 minus 1 is negative 1. The absolute value of negative 1 is 1, and 1 plus 3 is 4. Then if I run 1 through the function, 1 minus 1 is 0. 0 plus 3 is 3. Then if I run 2 through the function, I get 2 minus 1 is 1. The absolute value of 1 is 1. And then 1 plus 3 is 4. Okay, so that's where the turnaround is starting to happen. Alright, so I've got negative 2, 6. Negative 1, 5. Oh. 0, 4. 1, 3. And 2, 4. Now, if I were to run 3 through the function, 3 minus 1 is 2. Absolute value of 2 is 2. 2 plus 3 is 5. You'll see that this is going to start increasing again. So this side will go up like that. This side is going to go up like that. So again, the domain is negative infinity to positive infinity. The range, the lowest this goes, is 3. And it goes up to positive infinity again. Alright, the vertex, that turnaround point is at 1, 3. Which, if you notice, 1, 3, I hope that's starting to make some sense to you. We told you that the h value is what shifts things left to right, and the measurement of things that are left to right is the x-coordinate. The k value, we said, was what shifted things up and down, and what goes up and down is y values. So the h value, if you take the opposite of the h value, that'll give you the x value of your vertex. So if it's minus 1, it'll be positive 1. The k value, whatever that last number is after the absolute value sign, that'll give you the y value of the vertex. So the slope to the right of the vertex is going to be positive 1. The slope to the left of the vertex, it's going down by 1. So if we were to make that into a piecewise, we would say f of x is equal to x plus 3 for x's, we should probably do negative x plus 3 for x's less than or equal to 1, and positive x plus 3 for x's greater than or equal to 1. Oh wait, not quite true. If you think about it, this one has a y-intercept of 4, and this one has a y-intercept, would have a y-intercept, you can see, of 2. So there we go. That's a better piecewise function. It didn't ask for it, but just wanted to put it on there. So on the line below, describe the transformations using 3 of the following words for this graph of negative 2 absolute value of x plus 1. Well, let's go ahead and make a table of that. negative 2, absolute value of x plus 1. So, again, we will just pick some random points here. Negative 2, negative 1, 0, 1, 2. Let's go ahead and do negative 3 and positive 3 too, just for fun. Negative 3 plus 1 is negative 2. The absolute value of negative 2 is 2. And negative 2 times 2 is negative 4. Negative 2 plus 1 is negative 1. The absolute value of negative 1 is 1. And 1 times negative 2 is negative 2. Negative 1 plus 1 is 0. The absolute value of 0 is 0. And negative 2 times 0 is 0. Then 0 plus 1 is 1. 1 times negative 2 is negative 2. And then 1 plus 1 is 2. 2 times negative 2 is negative 4. 2 plus 1 is 3. Absolute value of 3 is 3. 3 times negative 2 is negative 6. And 3 plus 1 is 4. The absolute value of 4 is 4. 4 times negative 2 is negative 8. So I got a whole bunch of points here to plot, starting with negative 3, negative 4, negative 2, negative 2, negative 1, 0, 0, negative 2. Oh, did that the wrong way. Sorry about that. 0, negative 2, 1, negative 4, 2, negative 6, 3, negative 8. So you'll see this forms a V shape still, but this time it opens down. So this one is, we would say it is reflected. Reflected across the x-axis. Right? Because instead of opening up, it's opening down. Now you'll notice this one also opens up with like a slope of negative 2 instead of a slope of 1. So we would call that stretched. And you'll notice that the vertex is at negative 1, 0, so it is shifted to the left. So those are our three transformations. So the domain of this graph, again, negative infinity to positive infinity. In the range, we start at negative infinity and we go up to 0. The vertex is just that ordered pair of negative 1, 0. Now, the slope to the right of the vertex is going to have a slope of negative 2. Sorry, the slope to the left of the vertex would be positive 2. So if we're going to make a piecewise function of this graph, we would say f of x is equal to, and then we would say 2x, and it would have a y-intercept of 2, so plus 2, for x is less than or equal to negative 1, and you would say negative 2x minus 2 for x is greater than or equal to negative 1. And that's how we would graph that as a piecewise function. Alright, that's it for today. If you have any questions, just give me a shout out or an email or a message on Canvas, and I will be happy to help you out.